Now, what we're picking up with is considered a biconditional statement, because we talked about the conditional, inverse, converse, and contrapositive last week. And y'all found those to not be too bad. It was essentially more tedious than it was anything else, because we end up writing the same statement 4 times. Now, whenever we have a biconditional statement and its converse are both true. Sorry. When a conditional statement and its converse are both true, you can write them as a single biconditional statement. A biconditional statement is a statement that contains the phrase if and only if. If and only if. So if we have the conditional, P implies Q, and our converse, Q implies P, and both of these are true, then we can write it as a biconditional statement. Now, most of the statements that we had on Friday, really most of them worked one way or the other. Either the conditional statement was true or the converse was true. We didn't have a statement, too many statements where they were both true. But a biconditional statement will work both ways every single time. Now, on the homework, you did have some that would be considered biconditional, because if you got to it, it was one of the statements, if then, was if two angles add up to 90 degrees, then they are supplementary. Well, the other way was be if two angles are supplementary, complementary, then they add up to be 90. Supplementary would be 180. Because that would work both ways. If two angles add up to be 90, then they're complementary. If two angles are complementary, then they add up to be 90 degrees. That works both ways, so it would be considered biconditional. Are you ready for the next slide? Rewrite the definition of perpendicular lines as a single biconditional statement. If two lines intersect to form a right angle, then they are perpendicular lines. Well, if two lines are perpendicular, then they intersect to form right angles. That works both ways, yes? So, now if we look back at this, because it contains the phrase what? If and only if. That means if it is a biconditional statement, I'm not going to start it with if, and I'm not going to have then in the middle. So we won't have the if and the then anymore. Because what does it say? Well, two lines intersect to form right angles. Well, have we changed anything so far? Well, no, we dropped the if, we got rid of if. But two lines intersects to form right angles what? If and only if what? They are perpendicular lines. Two lines intersect to form right angles if and only if they're perpendicular lines. Could we have phrased it the other way? Well, we could have, but we'd have to change it a little bit, because we could say two lines are perpendicular if and only if the two lines intersect to form right angles. Because we'd have to add the fact that two lines are perpendicular if and only if they intersect to form right angles. But we could do it either way, because again, if it's biconditional, both ways are true. Questions on this here? Write a biconditional statement. If an angle is a right angle, then its measure is 90 degrees. Well, that is true, yes? If an angle measures 90 degrees, then it is a right angle. Well, yes, that would also be true, wouldn't it? Because a right angle means it's 90 degrees. If it's 90 degrees, it means it's a right angle. So how could we rewrite this as a biconditional statement? Okay. An angle with a measure of if it is a right angle. You don't have to write the second one. But either way works. Either way works. So like for your answer, I would take either one. They're both right. I think the first one sounds a little clunky, but it's still saying the same thing, isn't it? Yeah, so either way works. Questions on this here? Rewrite the definition as a biconditional statement. If two line segments have the same length, then they are congruent segments. So how can we do it? So what? Two line segments. Have the same length if and only if they are but only if they are congruent. Because if they are congruent, then they have the same length. If they have the same length, it means that they are congruent. Now, these will work with most statements, but not all statements. Because if we think back to Friday, we had the statement of if an angle is 30 degrees, then it is an acute angle. Would that work the other direction? If an angle is an acute angle, then it is 30 degrees. Well, no, we have other angles that are acute that are not 30 degrees. So this will work for some. The same thing is true for obtuse angles. If an angle is 120 degrees, then it's obtuse. Well, that is true. But if an angle is obtuse, then it's 120 degrees. Well, no, just like with acute, there's more angles. Do we have any other questions on this here? Well, this statement work both ways. If you can run for president, then you're at least 35 years old. If you're at least 35 years old, then you can run for president. Well, yes, that works both ways because according to the U.S. Constitution, I believe it's Constitution, but you have to be at least 35 years old to run for president. So this here, they do have two statements, yes? And we want to make it a single biconditional statement. So what are the two main parts? Well, let me get a highlighter. Well, we have you can run for president, yes? Because that's the hypothesis of the first one. Then we have, you can run for president as the conclusion of the second one, yes? But are those the same statement? Yeah. The conclusion of the first statement was you're at least 35 years old. The hypothesis of the other one is you're at least 35 years old. So that's one way that we can write this as a single biconditional statement. Yes. Now this is one of the few that does, this works the best. Because it is true both ways. If you're at least 35 years old, then you can run for president. You're at least 35 years old, and if and only if you can run for president. That just sounds funny. We would have to really change the wording to get it to make more sense. Because in two if-then statements, okay, they work both ways. We can see that. But if and only if, this is really kind of the better way to phrase it, because it'd be a little awkward to have it go the other direction. You're at least 35 years old if and only if you can run for president. It just seems weird. Let's look at this one here. If Mary's in theater class, then she will be in the fall play. If Mary's in the fall play, then she will be in theater class. So are these two the same statement? Essentially, they changed the wording a little bit. But they're both true. If Mary's in the theater class, then she will be in the fall play. If that is a requirement of being in theater class. If Mary's in the fall play, then she must be in the theater class. Why not? Let's grab a highlighter. Mary's in theater class. She must be taking theater class. Be in the fall play. Is in the fall play. So how can we write this? And I don't know why, but something in me wants to put a V there. Theater class if and only if she is in the fall play. Mary's in the theater class if and only if she's in the fall play. Because we could have gone the other direction and said Mary's in the fall play if and only if she's in the theater class. So this one here works a little bit better going both ways, unlike the president one on the last one. Any questions on this here? All right. Truth tables. Making a truth table. This here kind of helps us get an idea of how the overall statements can go, given P and Q. And P and Q are just any statement. Now, P can be true or P can be false. I mean, it has one of those two options, yes? But Q could also be true and Q could also be false. Because we could have this setup where both P and Q are both true, yes? But we'd also have the case where P is true and Q is false. And then we can also have the case where Q is true and P is true, or Q is false and P is true, or Q is false and T is true. Well, if P is true and Q is true, then the whole statement should be true. If our hypothesis is true and the conclusion is false, the whole thing is false. If the hypothesis is false and the conclusion is true, the whole thing would be true. And if the hypothesis is false and the conclusion is true, the whole thing is true. If you start out with a false hypothesis, it doesn't mean anything. It ends up being true anyways, because it really doesn't tell you anything. So the real one that when proving mathematically, focus on, you don't have to circle this, I'm going to circle it, is this statement here. If we're going to go about proving something, we always assume the hypothesis is true. Because even with the scientific method, y'all covered that in 8th grade, yes? Because if you went to and made a hypothesis and then tested it, well, if the test turned out to make the thing false, that your original hypothesis was false, what'd you do? You change the hypothesis and try it again, yes? Because we need this hypothesis to be true, otherwise it doesn't tell us anything. So we can actually use these to see how the overall statements work. Well, again, with P, we said we could have two truths. Because we could have true and true, true and false, false and true, and false and false. Now, I did go on and list the conditional statement up there next to it. Now, if we have true and true, the whole statement would be true. If we have true and false, true implies false, the whole thing would be Yep, sorry. This P and Q are flipped. So false, let me actually write that in. Because true implies true, false implies true, as we saw for the conditional statement is true. The next one would be true implies false, which would be false. And the last one, false implies false, would be true. Well, the conditional was true, false, true, true. And we said the converse is the flip of the conditional statement. We flipped it. True, false, true, true is now true, true, false, true. We flipped it. Well, we're going to look at the inverse next. I'm writing these up here just so that y'all can see them. You don't have to rewrite out those, the conditional and the converse. Now, not P means the opposite, because whenever we take the not of something, it's the opposite. So P was true, true, false, false. So not P would be false, false, true, true. Because true becomes false and false becomes true. And Q was true, false, true, false, false, true, false, true. We flip it. Now, luckily, we don't have to think of this one backwards because we're saying not P implies not Q. So our first one is false implies false would be true. False implies true is true, because it's the weird one, because if the hypothesis is false, it's always going to be true. True implies false would be false, and the last one would be true. Does that look similar to one we already have? It matches up with what? The converse. And as we said on Friday, the truth value of the converse will always be the same as the inverse. They will always work out to be the same. Any questions on this here? The last one we had was the contrapositive. Now, what we talked about last week is it's going to be the same as the conditional, because the conditional statement and the converse we said would always have the same truth value. So what we should expect to see is true, false, true, true. Now let's see if we get that. Now not Q, so true, false will be false, true, false, true. Not P would be false, false, true, true. Well, not Q implies not P, so false implying false would be true. True implying false would be false. False implies true is, and true implies true is true. Does it match up with our conditional statement? So this is just a way for us to see that these do line up. Questions on this here? We're going to do one of these together. We're going to make a truth table for P implies not Q. Okay. So we'll have P, Q, and not Q. And then P implies not Q. Well, the four values we'd have for P are true, true, false, false. Because it's easy to list those out. Q, true, false, true, false. Because we do have it set up so we have true and true, true and false, false and true, and false and false. But we don't want just Q, we want not Q. So we would take this as false, true, false, true. Now we really just wrote the middle one in so that we can get not Q, get an idea of what not Q would be. So our first statement is true, false. True hypothesis, false conclusion would be false. Because the only way that we get true is if they're both true or the hypothesis is false. So true implies true would be true. False implies false is true. Because again, anytime the hypothesis is false, the whole thing is true. And false implies true is true. Questions on this here? I'm going to go on and let you have your assignment. On page 66, problems 29 through 38. 29 through 38, all. Ten problems.